Thank you, guys. I hope this is the last session. I hope it will be not too long, and hopefully I'll provide some more insightful information to you guys. So let's talk about what are the things that we are going to cover in this talk. So I'm going to provide some context around the streaming infrastructure, and then what is the streaming platform tech stack looks like at Lyft, and then what is the current pipeline architecture and tools around the whole streaming infrastructure, as well as the application which are using streaming infrastructure. And then at the very end, I will talk about the lesson that we have learned while developing the streaming infrastructure as well as the applications. And at the very end, I will have a Q&A session. So if you have any question, please feel free to ask during that session. So context, for those who do not know what is Lyft, so Lyft is a ride-sharing company. The goal of the company is basically to match driver and passenger. And we also want to make these people, like the driver and passenger, happy. We want to match them in real time. In order to do that, we have to provide a very short ETA, consistent pricing, and fair driver warning for the drivers, as well as timely notification. All these things can be done in real time only if you're making all these decisions in real time, right? So in other words, what I'm trying to say is that this streaming infrastructure is the backbone of the business critical product at Lyft. Let's dive deep into some of the use cases, and then we will look into the whole streaming infrastructure at Lyft. So some of the use cases, so very first one is the feature generation pipelines. So as you may know, that some of the use cases at Lyft, they required machine learning infrastructure. And for machine learning infrastructure or machine learning models, one of the key ingredients is basically the feature. And these features are also generated by all these streaming pipelines. So one of the use cases is basically the feature generation pipeline. And I also want to club the other use cases where you're just ingesting the data from the streaming or PubSub infrastructure and then indexing it somewhere. So both of these use cases are very much similar, so I'm just clubbing them together into this. So at Lyft, what you have is like this kind of pipeline. They're getting all these data from Kinesis. So we are using AWS services Kinesis, which is providing all this data. So different services, our own microservices plus the driver app, passenger app, all of them are their data or events, they are indexed in Kinesis. And from there, we get it to our ingestion pipelines. So these ingestion pipelines are basically, they are processing this data at the very high scale. And then they are trying to filter out all those invalid data. And then they are trying to enhance that, like they are trying to validate and enhance the data and then pass it on to the other pipelines that is called aggregation pipeline. So aggregation pipeline are more kind of a pipeline which has their own custom logic or product logic, which is generating or aggregating the data and generating data for the model, which is then passed on to the either feature store or Kafka topic. Depending on what is the use case for the end user or product. Say for example, if there is any kind of synchronous use case, one example could be fraud. So when you want to detect fraud, you want to access all those features in real time or in synchronous mode rather than the asynchronous mode. In that case, fraud service will be querying all these feature stores, trying to get the data or different vectors in real time or in synchronous mode and process it. So for that use case, like we use feature store. For other use cases, for example, where values can be computed in asynchronous mode, right? For those use cases, we just publish it to Kafka topic. So other pipeline, or I would say other product pipelines, could ingest this data from there and then compute the values. One example could be pricing, dynamic pricing, right? So dynamic pricing is calculated based on the region or the area in which there's an imbalance of demand and supply. It cannot be computed for session-wise, right? So for those kind of use cases where things are computed in asynchronous mode, we use the data from the Kafka topic. Then the other use case could be the model training pipelines. There are different use cases where we want to train a model in almost real time. When I say almost real time, it is basically varying from 30 seconds to almost half an hour. And if you're going beyond half an hour, it is more kind of an offline job. But yeah, like if there are use cases which require to train a model in real time, then we use these pipelines as well. And these pipeline can have, what do you call it? So these are, these are model training pipelines. So model training pipeline are getting the data in real time, and then these models are trained, and then we upload that artifact or trained model to the model repository. One example could be that we need to forecast certain values or market condition in real time, like how the demand and supply values are changing in a given minute or so. We cannot do in offline. If we just do in offline, then the accuracy of the data will be very, it can vary a lot, and we may not be able to quickly predict the values. So some of the online forecasting models, they use this infrastructure to basically train their model and also serve the model. The other similar use case is like model inference pipeline. As I had mentioned earlier, some of the use cases where you need to inference the model or run the model in real time or in asynchronous mode, there we use it. And one example was prime time or what we call search prices. One interesting thing about this model inference pipeline, in some use cases, there could be a DAG of models. That means one model input could be dependent on the other model. So in other words, you can think of different layers of models. The very first layer will receive the data, it will compute certain variable, and then it has to pass on to the next layer of the model. The next or the final layer will be basically computing the value. For instance, there are like even prime time or search prices model, there are different models which are computing like conversions, what will be the forecasted value and all those things. And ultimately, the pricing model will get all these inputs and then it will compute the prime time. So in that case, it is very important that the data dependency, those are met, and also consistency is also met. If they do not meet, then whatever the value that we will be computing or predict, that will not be accurate. And then our marketplace will not be very efficient. So in that case, streaming also comes very handy, and it computes, like it ensures that the data completeness and the consistency is maintained. And then once the model inference is done, then it publishes the data to either the teaser services, which can further serve that value to other service or downstream services, or even the Kafka topic here. So these were like some of the use cases. Now we can talk about the streaming platform tech stack. So in simple, what do you call our 10 or 20,000 feet view is this one. Like at the very bottom, we have Amazon Web Services. On top of it, we have core infrastructure. Core infrastructure is ensuring how the orchestration and everything is done. And then on top of it, there are streaming infrastructure, which consists of PubSub plus other streaming app. And then you have platform tools. And I will talk more about the platform tools in whatever different tools that we developed at Lyft. And on the top of it is like we have Flink app and Beam app. And then the other like product teams or even the platform teams, they develop their own tool on top of it. So, and then at the very high level, like if we have to imagine how the whole streaming infrastructure fits into the whole ecosystem, this is how it looks like. From the very beginning, we have the different services which are basically generating analytics events. They get pushed into one kind of a global bus or Kinesis stream. And then you have KCL app. So KCL app is basically, it's for fan out. So basically what you have is like you cannot subscribe to a kind of a global, PubSub and ingest it. Like in that case, like you will be most probably dropping like 80 or 90% of data, and you will be interested in the data which is required by your application logic, right? So what we have done is like KCL app, which its main responsibility is to just provide only relevant data to the Kinesis stream, which is further ingested by the application. And then you can have a data ingestion and enrichment pipeline, which is basically further processing that raw data and then passing it on to another Kafka topic. And then at the very end, you have the aggregation pipeline or other business specific pipeline, which are further processing the data and then passing on to either feature store, Kafka topic. You might be wondering that there is a kind of hybrid over here. In some cases, you can see that there are Kinesis stream and in some cases Kafka. It is because of the, historical reason. When we started developing our app, we started with the AWS and we just used the AWS services. And that, we just used Kinesis. At that time, Kafka was not that popular. And then gradually we started adopting it. And for the newer application, we started using Kafka. So we gradually moved to Kafka. And hopefully in one day, we will just replace Kinesis with Kafka. And one more thing to note over here, the Fanner or fan-out service is also publishing into both Kinesis and Kafka, depending on the use case. Or if it is a newer use case, this is most probably we are publishing into the Kafka. But if there is the older use case, then it is basically all the downstream one, they are ingesting it from the Kinesis, so that's why we have to publish it to Kinesis. Then let's talk about the scale at what we are currently working on. So we are powering the business critical product like dynamic pricing, driver incentive, real-time supply management. And then we are also computing ETA, determining driver routing, making dispatch decision, and all of them are done for all the session in real time. Then we are computing dynamic pricings for almost tens of millions of geohashes every minute or so. And then we are forecasting different marketplace parameter for 640 cities for the USA and in 12 plus cities in Canada. And we are also computing driver incentive in real time for not 100, but it's 1 million hotspot per minute. And one thing that I wanted to mention over here, 40 to 50% of the product are directly using streaming, whereas almost 100% of the services are indirectly using streaming as well. So if any data is getting generated in our system, eventually they hit the streaming services for sure. And then as this talk is about evolution, so I'm going to talk about how our pipelines they evolved. So when we started streaming, it was very new at Lyft and we did not have any prior experience. So we started with the MVP of migrating a whole marketplace use cases to a kind of streaming app. So what we did is we just built one MVP pipeline where you ingest all these events and you also orchestrate the model in one single pipeline. And then that pipeline would just compute the decision variable and publish it to the internal services. It will be great. For initial rollout, it worked fine. We roll out a couple of region, but we soon realized that it will not scale well for the Lyft scale or Lyft traffic. There were many, I would say at least 4 or 5 challenges. One is that as you can imagine, that the pipeline which is ingesting all these events, right, and processing them, filtering them, right, it's very process heavy, or it is basically getting millions of events per minute or so, and it is processing it. Whereas the model execution part, it is lighter. That means once the event processing is done, once the aggregation is done, the data is aggregated, right? So in terms of, if you look at the number of messages or the size, the number of messages may decrease significantly, but the size may increase. But model execution is more about the orchestration, how you're passing data from one model to other and how you're orchestrating that one. So the performance characteristics of these parts are completely different, and having in one pipeline does not make sense. Then the other challenge is that, when you're trying to scale or trying to tune the parameters for the performance, it does not work at all. You will get suboptimal performance, but not you will not be able to squeeze out on the performance from this one. If you have both of them in one pipeline. And then there are other challenges as well. So we work on cities, and most of cities, like I would say 10 of the cities, like San Francisco, Los Angeles, New York City. These are the cities which are top cities which are generating 80% of the data. So if you do not architect the pipeline correctly, you will have the data skewness problem. And if you have the data skewness problem, then you will be wasting your resources and also increasing the end-to-end latency. And in this case, like when you're trying to optimize it, it will block you in a way. It will not, you will not be able to optimize this pipeline, right? And then we also observed some other issues, and those were not related with the engineering, but more on the operational side. So when you're developing any feature, the feature development is very front heavy. That means once you develop the feature and roll out, we are not going to make those many changes in that pipeline. But whereas the model development, like it is constantly you are iterating over that one. You are releasing a new model version, and you're constantly releasing it, right? If you're doing so, that means you have to deploy the whole pipeline again and again, and it does not work. Sometimes something will break, and then it will be hard for you to figure it out what happened, whether it was broken because of the feature or whether it was broken because of the new model. So just separating them out would make more sense. And also, since the very first stage of the pipeline is generating feature, and it is very internal to the pipeline, so it does not share the data with any other model or any other product. If you have to develop a product which should be consuming the same data, you have to rewrite the whole pipeline again, right? Then in that way, what you're doing is you're also wasting your development time and also resources, right? So there was, so there were such kind of issues. So we thought, we went back to drawing board, what is the different ways of basically addressing all these problems. Then we came up with this design. Basically, we divided the pipeline into two. One is mainly for the feature generation, and the other one is more model execution. So now, once you build the feature generation pipeline, it is set, it is running, and you can tune it according to its performance profile, right? And it will respond to those tuning as well. And this was mainly tuned for the higher performance or higher throughput, where you're ingesting millions of events, processing them really fast, and then generating the aggregated results. And then you have the model execution pipeline separately. So what happens there? You are not processing those many events, since all of the data is aggregated, so you have less number of events, but you're more focusing on the data consistency, and you're mainly focusing on the data consistency and the dependency management. And since you are publishing it to the Kafka topic, now you can have many more model execution pipeline, and if they want the same data, they can just hook up to the Kafka topic and they can ingest it. So, and this one is having a PubSub method. So the model execution pipeline does not have to worry about from where they are getting the data, and they just need to know the Kafka topic, and they just need to hook up to that one. And another advantage is you can scale the individual pipeline according to your need. You do not have to worry about the other. And they have different development cycles, so you can develop or make modification, and you can roll it out changes without worrying about the other pipelines. But this scaled well, and we were able to roll out to all cities and everywhere. But after running for a couple of months, we realized other operational challenges with this one as well. So when we replicate the feature, we realized that the feature pipeline, we realized that most of the logic, I would say 80% of the logic was kind of duplicated, it has the same, even validation, even filtering and all those things. And only the 10% of the logic, which basically aggregates the event, that is different, right? And in a way, when you're replicating all these pipeline, you are kind of wasting it, wasting the resources, right? You can push out all these data validation, data filtering to the boundary of the system. So that way you validate the data, drop the data, invalid data early on, and then pass it on to the different services of the pipeline, right? So that way you can further reduce the operational cost. So that's what we did. And there was one more challenge that we also faced. Basically, when we are ingesting pipeline and there are different pipelines, They are just processing on that individual event or data. They do not have the full context about users, say for example, driver and passenger. So the system does not know about it, like the whole life cycle of that one. So building any other contextual aware product could be harder for this pipeline, right? So what we did is we divide that feature generation pipeline further into two sections. One is the data ingestion section and enrichment pipeline, and the other one is aggregation pipeline. So data ingestion and enrichment pipeline is basically ingesting all these data. It has basically a state machine, basically it is ingesting all these data and building a kind of state machine. It knows the history of the user, whether it's a passenger or driver, it knows about that one. And then it has the right granularity of history plus the context, so the downstream application services can make their decision on that one. One example could be, say for example, driver incentive. We want to know like how many drivers are not getting enough rides in the last like half an hour, and we want to incentivize them providing more rides. If you consider the older pipeline, it does not have the context about that one. It just knows that, okay, this driver is ideal for less, like this driver is, free for this minute, but it does not know about the previous history. But using this pipeline where we are tagging the data, we are keeping the history and then passing out to the application, the downstream application knows that, okay, this driver was, free for last 30 minutes or so, and he has not got any rides, so we need to incentivize it. So we were able to build that kind of product based on this pipeline. And the another one is like, since all these processing, the heavy lifting or data ingestion and enrichment is done in one pipeline, so you have centralized in one place and you're not repeating yourself. So that way you are also saving infrastructure cost. Cool. Let's talk more about tools. What are the tools that we developed? When we started developing the pipeline, we also realized that this pipeline is different than the microservices. Microservices, you can roll it out per AZ, and if there is any problem, you can roll it back quickly without affecting the entire production, right? But the streaming pipelines are different. They are like binary, either 0 or 1. Either they will be rolled out to everywhere or not rolled out at all. And when you roll it out to everywhere and you see any kind of problem, it's kind of too late. Like you may be, you will be affecting the production system or products, right? And they could be down for several minutes or so, which is not acceptable at Lyft scale. So what we did is like we build a kind of a concept called validation pipeline. So it is basically a parallel production pipeline, which ingests the production data, but it reads the data from various sources, but it does not write anywhere. So though it is ingesting the production information or data, but it does not affect any other services or downstream services. So in a way, you can safely test out your changes in production without affecting the production. And when you are able to do that, that means you have a very high confidence that when you roll out your changes, that this change will work in production. And there is a very simple way we did it, basically having one flag in the pipeline, which indicates whether this is a validation pipeline or not. And there is one filter at the very end of the pipeline. If the flag is on, that means it will not send the data to sync. And we were able to, at least 99% of the error, we were able to catch it in the development phase itself. And in some cases, like when we tested all our changes in staging, in some cases it will work, but when you go at production, it will not work at all, mainly because there's a huge data skewness that we did not consider while designing the pipeline. But if you're able to test the pipeline in production, you are able to identify all such issues during the development phase itself. And that also provides you kind of, the higher reliability of the pipeline. Then you would say like, okay, we have the validation pipeline, that's great, like, but it's still manual. Like what happens if you merge your changes, should it get auto deploy or not? Like initially we had a kind of manual way of like deploying the pipeline, but it's not scalable, right? Like you have to, watch the pipeline. Even though you have tested out in validation pipeline, you have a good confidence, but still you have to deploy it manually. So what we did is like we built a kind of a safe deploy mechanism. So safe deploy is also integrated well with the KRS operator that we had released earlier. So basically what does it do is it takes the safe point and check safe pointing and then try to roll it out the pipeline. And if the pipeline health is degraded once the newer version is rolled out, then it automatically rolls back the changes. And also it tests out the changes in validation pipeline, and then it goes on production. So if there is any failure, like you will see it on the validation pipeline first, and then it will not even move forward. Yeah, and even in some cases where we may have missed in validation pipeline because of some special configuration only for validation pipeline and not for production, you go on production and it will detect that issue and then it will automatically roll back. So you can have the auto deploy enable for that pipeline, and you can like auto deploy enable, and still it will ensure that like it will not bring down the application because of the bad changes. And this also increases the product engineering or developer productivity, because now you do not have to manually deploy anything. Like once everything's tested, you just merge it to master, it will get deployed automatically. Then another thing that we did is optimizing capacities. So sometimes like when people build a pipeline, right, they provide certain configuration, and it may not be efficient. For example, in this case, right, like where we have provided like 8-core CPU and memory is like 50 gig, which is not a multiple of 8, and it is also not in good for good bin packing. That means on any kind of a Kubernetes node, if you're trying to get this one, like there will be more fragmentation. In a way, that fragmented part will be wasted, right? Anyway, we will be paying for that one, but it will not be used, right? So what we did is like we built the streaming platform, basically build the kind of mechanism of like detecting such kind of not very efficient configuration, and automatically update that to the nearest best configuration. So as you can see in this, in the top image, right, like it is requesting for 8 CPU and 50 gigs, but it is not efficient. So what it is doing is it is automatically updating it to the 8-core machine as well as 64 gig, which is a multiple of 8. And this has worked well. In many cases, we had built something similar as well. We realized that people will not completely understand the configuration, because especially in streaming or Flink application, there are many more levers for performance configuration, and people do not understand all of them. So it's better to build some kind of tool which prevents some kind of inefficient configuration, and not manually, but automatically applying the best configuration automatically, and also educate the customer that, okay, you have made some mistakes over here, but we are correcting it for you, and then we are deploying it. So even they can if they can also look at the configuration, what is the final configuration, they can also update it in their repository. Then, so when we build all these pipelines, we made it easier for them. And the product teams is generally, they have data scientists as well, machine learning model engineers. They are more focused on the data and how to build the models. They are less worried about how you're getting the data, how you're building the pipeline. And if you ask them to go and understand the intricacies of building a pipeline, they will not be very happy about it, right? So, and also it requires more effort to basically completely understand all these intricacies and build a kind of right pipeline. So what we try to do is like, we try to abstract out this information, and we thought we'll make it easier for ML engineers and data engineers to build a pipeline by themselves. So we do not have to involve an engineer to build a pipeline. Data scientists and ML engineer can build by themselves. What we did is basically we build a kind of ML-based configuration-based pipeline. So you can see the example over here where you can, in the YAML configuration, you can write different stages of the pipeline, and you can provide your UTF. We also provide our own UDF where like most of the general purpose functionalities are available. And if they have their very special use cases or, very highly customized UDF, they can define it and also use it over here. So that further reduced the development time. So now they can just focus only on their business logic or defining that UDF and using it. So this reduced, creating what we call development cycle for a pipeline from weeks to a couple of days or so. So that basically increased the product, the developer productivity. And this also helped us to scale well, like to support many more use cases and like iterate faster. So yeah, like we built all these platform and tools, but I don't think it was a kind of an easy task or like very smooth sailing, right? Along the way, we made several mistakes and we learned our lesson. So some of the lesson learned is basically standardization. So when you open this platform or, even the application platform to different engineers, they are not the expert, right? They may be making mistakes. They will be using something which is not, preferred by other engineers or, platform engineers. And they can, like the other engineers can go crazy. They will use whatever they want to use, right? So, and it's kind of harder for them also, right, to manage this. So one way what we did is like we try to standardize everything. Even if you're defining the feature, what should be the feature name, how it should be formatted, where it should be indexed. Even the Kafka source and Kafka sync, Kinesis source and things, like common operator, we try to standardize it. So that way there's a standard way of like accessing it. Instead of they using different clients to get the same job done, we try to standardize all of them so that there's one way of like doing it. There should not be many ways of doing it. If you're doing that way, that means you are increasing the surface area and then you are creating overhead for your teams, or it will just increase the operational burden for the team. So what we did is we tried to standardize all of them. And then we also provided better abstraction for usability. That means we try to focus on like making simple for the user and ML engineer so they can focus on the business logic rather than focusing more on the intricacies of building the pipeline. And because of that, we built the YAML-based configuration pipeline so that made it simple. They don't have to understand how joining and everything will work. It will be taken care by the underlying infrastructure. But this helped to basically scale well. It basically made easy to build a pipeline. And when you make easy to build a pipeline, people will go crazy and then they will start using for random things without understanding it, right? So that's another problem that we had. So for that, what we did is basically we created guidelines. Like what are the things that you should be doing and what are the things that you should be avoiding. So having a guideline about even for like how you're keying the data. So as I had mentioned earlier that like some of the top cities are generating almost 80% of the data that is most likely caused skewness. If they are using key region or city as key, most likely that pipeline will have data skewness, and then we will be banging our head like why there's a data skewness, why there's a high latency, right? So even having such kind of guideline mentioning about like if you use so, you will run into that problem, so avoid it. Just having it documented and also educating them helps a lot, and they do not make all these mistakes, and they like while designing the pipeline, they avoid all these mistakes. So that way you also, like avoid all this mistake and you can develop the pipeline faster and avoid future headaches as well. The other one is observability. And I would say observability is most important for any pipeline or any production systems. For us, like we had to work really closely and we had to channel in the Flink and Bean related matrices to our system so that we can observe, like we can have our business logic matrix as well as the system level metrics in one single dashboard. So that way it is way easier to identify any problem. One example could be we had data skewness parameters as well on the dashboard. So if there is any problem, maybe people missed the data skewness while designing the pipeline, but it will resurface it on the dashboard, and it's much easier to identify if the data is skewness or something. If we hadn't have that kind of a dashboard in place, it would be really hard to basically go and check everything and figure out what's going on, why there is a latency, or why certain tasks are taking more CPUs or memory. So we built that one. Another learning one is blue and green deployment. And I think most of you might be aware about blue and green deployment for services, but even we had it in the pipeline. Initially, we thought that this will provide a kind of better reliability, mainly because you have one version of pipeline running and you deploy the other version of pipeline, and if other version does not look good, you terminate it, it's fine, right? But it caused more headache, operational headache. We had to basically build customized logic for the monitoring to identify such kind of cases. And also, like when you have a blue-green, it's kind of a hard way of it makes the system more complex. And also, you will not be able to avoid duplicate data. Even though we had a system in place which will ensure that there is no duplicate data, but it was unnecessary complexity. So what we did is we removed that blue-green deployment. Though it is part of the KRS operator released by us, but we have deprecated that field and we went with the safe deploy, which is better than the blue-green deployment. I think that is it.